This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome to Chapter 1 of our series, Chemistry of Everyday Life, where today's episode is titled Atoms and Molecules, the Building Blocks. Get ready to uncover the fundamental structures that make up everything around us, from the tiniest particles to the complex compounds we encounter daily. Let's dive in. Right now, you're breathing in a gas that makes up about 1/5 of Earth's air, yet you can't see, taste, or smell its tiny building blocks. In this episode, we'll step inside that invisible world and uncover what your lungs, your phone, and your coffee mug secretly share. That same hidden world quietly controls your everyday experience. The sharp scent of a peeled orange, molecules of limonene hitting receptors in your nose, the rigid screen on your phone, silicon and oxygen atoms locked into an orderly crystal. Even the heat from a cup of tea is just atoms jostling faster as they gain energy. To work with matter, whether you're cooking pasta, charging a battery, or designing a drug, you're really working with the way atoms connect and move. A single drop of water contains roughly 10 square 2-point molecules, each with a precise shape that helps it cling to surfaces, dissolve salts, and transport nutrients in your body. Chemistry's power comes from numbers like these. In this episode, you'll learn how to count the uncountable using moles, how molecular shape controls behavior, and how tiny mass differences shape life's big outcomes. Chemists zoom in even further, past what you can see or smell, to track which specific atoms show up and in what ratios. Your body, for example, is roughly 65% oxygen and 18% carbon by mass, but by atom count, it's dominated by lighter elements, about 63% hydrogen, 20% oxygen, 10% carbon, and 3% nitrogen. These four alone make up 96% of the atoms in living things. Change their arrangement, and you change the substance. C2H6O can be drinkable ethanol or poisonous dimethyl ether, depending on how the same 9 atoms are connected in space. To make sense of so many tiny particles, chemists needed a counting shortcut. That's where the mole comes in. 1 mole is exactly 6.022 times 10 square 2-point particles, about 602,200,000,000,000 jillion. If you had 1 mole of grains of sand, they could cover all Earth's beaches in layers thousands of meters deep. Yet 1 mole of water is just 18 grams, less than a tablespoon. Why 6.022 times 10 square 2-point? It's chosen so that the mass of 1 mole of atoms in grams matches the average mass of a single atom in atomic mass units. Carbon-12 is defined as exactly 12 atomic mass units, U, so 1 mole of C12 atoms weighs exactly 12 grams. That link lets you go from, I weighed this, to, I know how many atoms are here, in one step. Suppose you dissolve 5.84 grams of table salt, NaCl, in water. Sodium is about 23 U, chlorine about 35.5 U, so NaCl is roughly 58.5 grams per mole. Divide 5.84 grams by 58.5 grams per mole, and you get 0.100 moles. Multiply by Avogadro's number, 0.100 times 6.022 times 10 square 2-point, approximately 6.0 times 10 square 2-point formula units of NaCl in the glass. Each of those consists of 1 Na- and 1 Cl-, so there are about 6.0 times 10 square 2-point of each ion moving around. Inside any solid or liquid, those particles aren't arranged randomly. The way they're packed and the kind of bonding controls properties you notice every day. In copper wire, metallic bonding allows about 10 square 2-point electrons per cubic centimeter to drift when you apply a voltage, which is why it conducts electricity so well. In contrast, in sugar crystals, each carbon-hydrogen-oxygen framework is covalently bound and electrically neutral. Almost no freely moving charges exist, so a sugar cube doesn't conduct. Shape also matters. The angle between bonds, the distances between nuclei, and how electrons are distributed create polar or nonpolar regions. A polar molecule can attract ions or other polar molecules. A non-polar one resists mixing with them. That's why a few drops of cooking oil, made mostly of long, non-polar hydrocarbon chains, stubbornly float on top of water instead of dispersing, even if you stir. At the nanoscale, empty space between nuclei doesn't mean weakness. Repulsive forces between overlapping electron clouds ramp up steeply when atoms are pushed too close. Press your hand on a table with 50 newtons of force, and trillions of such interactions push back to support you. A single sip of tap water, about 10 milliliters, contains roughly 3 times 10 to the 30,000 water molecules, more than the number of stars in the observable universe by a factor of about 10 million. Mixed in are dissolved ions. In moderately hard water, you might have around 2 times 10 to the 30,000 Southeaster pice and Malgin 3 pice ions in that same sip, enough to leave visible scale on a kettle after repeated heating. In a 250 milliliter cup of coffee, about 5 grams of dissolved substances, caffeine, organic acids, minerals, correspond to on the order of 10 to the 30,000 individual molecules, each interacting through specific bonds and shapes to create flavor. Stainless steel cutlery owes its rust resistance to a surface layer only a few atoms thick, roughly 2 to 3 times 10 to the 30 meters of chromium-rich oxide that self-repairs when scratched. Like a tightly woven raincoat that blocks large drops but lets air pass, this ultra-thin barrier stops further corrosion while still allowing the bulk metal to remain structurally strong. Designing matter from atoms up lets us program behavior instead of just discovering it. By tweaking a catalyst's atoms, chemists have cut some reactions' energy use by 50 to 80%. Single-atom catalysts, each active site just 0.1 nanometers, can turn CO2 into fuels with 90% selectivity. DNA-based nanorobots only 20 nanometers across have already targeted leukemia cells in mice, shrinking tumors by 45%. Ultra-thin coatings 1 to 5 nanometers thick can make glass repel germs, fog, or fingerprints without changing how it looks. Your challenge this week: spot chemistry in action 5 times a day. Note a phase change, a color shift, a smell, a fizz, or metal tarnish. Each event traces back to atoms rearranging by the quintillions. By day 7, you'll have logged at least 35 examples, enough to see patterns and start predicting what will happen next. This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!